My name is Me, and today I'll be talking about pyridine. Let's begin by learning a bit about pyridine structure. The chemical formula of pyridine is C5H5N, and it is a basic heterocyclic aromatic compound. A heterocyclic compound is a cyclic compound that contains atoms of at least two different elements. As you may have noticed, pyridine structure is similar to that of benzene. However, a methine group is now replaced by a nitrogen atom, giving this molecule properties similar to those of a tertiary amine. The double bonds in the ring are actually shared by all the atoms, which is also known as electron delocalization. This is depicted by the circle in the structural diagram. A lone pair exists on the nitrogen atom, making this molecule polar. Also, all the bonds within this molecule are covalent, which means that electrons are shared. In contrast to benzene, pyridine's nitrogen atom creates a dipole effect due to its lone pair, making the nitrogen atom slightly negative compared to the rest of the molecule. Nitrogen is more electronegative than carbon. Therefore, this dipole is the effect of more electrons being drawn toward the nitrogen atom rather than being shared equally. While benzene is non-polar, pyridine's lone pair makes it a polar molecule, and bond angles are slightly decreased due to this as well. Due to its polarity, pyridine is more soluble in water as polar molecules dissolve in polar solvents. As you can see in the following diagram, the negative nitrogen atom attracts the positive H atoms from water and forms the conjugate acid pyridinium, and releases hydroxide ions, making the solution basic. Here we can see the dissociation equation of pyridine in water and the structure of its conjugate acid, pyridinium. Now, let's do some math. Let's explore the effects of adding strong acids and bases to the weak base pyridine. Before we begin, let's take a look at the initial pH of pyridine at a concentration of 5 moles prior to adding anything. We start off with 5 moles pyridine, and we may safely assume that the initial concentrations of the conjugate acid and OH are 0. Since pyridine is a weak base, it has Kb value, which is 1.7 times 10 to the power of -9. Therefore, the resulting solution will be basic, and the ice table will have the general equation A negative will dissociate into HA and OH negative. So here we have our ice table, with our initial concentration of pyridine, which is 5 moles, and initial concentration of products as 0. For the change section of our ice table, we subtract x from the reactant side and add x on the product side. Now we may sub in our equilibrium values into the Kb formula, where the numerator consists of the products and the denominator consists of the reactants. We get the final equation 1.7 times 10 to the power of -9 equals x squared over 5 minus x, and now we may solve for x. Right away, you can notice that the 1000 rule is applicable since the Kb value is smaller than the initial concentration of pyridine by more than a factor of 1000. Since Kb is related to x, the 1000 rule tells us that x is extremely insignificant, allowing us to eliminate x from the denominator. The value of x won't have any significant change to the equilibrium concentration of pyridine. We get about 9.22 times 10 to the power of -5 moles for the value of x after all our calculations. Now x is substituted back into the ice table, and we now have our initial equilibrium concentrations prior to adding any acid or base to the solution. We may now use the negative log of the hydroxide concentration at equilibrium and then subtract it from 14 to attain the pH value. Our final answer for the pH is 9.96 for the initial concentration of 5 moles of pyridine. Now let's add a strong base. We will be adding 5 times 10 to the power of -5 moles of sodium hydroxide to the weak base pyridine. We can hypothesize that adding more base would increase the pH, making the solution more basic. Adding 5 times 10 to the power of -5 moles of NaOH will increase the amount of base, which is pyridine, by 5 times 10 to the power of -5 moles. Since more pyridine is created as NaOH reacts with the pyridinium ions, which is a conjugate acid, to form more pyridine. This also means that the amount of pyridinium ions will also decrease by the same amount as they're being used up to form pyridine. Using this logic, we can add the NaOH concentration to the reactant side and subtract it from the product side to achieve our equilibrium concentrations for A negative and HA. We may now sub in the A negative and HA values into the HH formula to find the pH. For our formula, we need the pKb value, the concentration of A, and the concentration of HA. We can negative log the Kb value from before to get the pKb, and then we may sub in all our values into the formula to find the pOH, since we started off with the base, and then subtract it from 14 to attain our final pH value of 10.3. You may notice that the pH only increased by a little despite adding a strong base. This is due to the buffer effect. A lot of the strong base was used up by the pyridinium ions to form pyridine, allowing only a little to contribute to the overall pH. Now let's see what happens when we add a concentration of NaOH almost reaching the initial pyridinium ion concentration. We can predict that the buffer effect will not exist anymore and the pH will increase by a significant amount. Using the same logic as before, the pyridine concentration will increase by the same amount of NaOH added, and the pyridinium ion concentration will decrease by the same amount of NaOH added, which is 9.21 times 10 to the power of -5. You can see that the equilibrium amount of HA is essentially 0 as it all gets used up by the strong base to form pyridine. We may now sub in our values into the HH equation. Our pKb remains the same as before as it's a constant value, only the A and HA values are different. After doing our calculations, we can get the final pH of 12.93 for 9.21 times 10 to the power of negative 5 moles of NaOH. As you can see, our prediction was correct, as the pH increased by a total of almost 3 units, indicating that there is no more buffer effect in play. Hence, the solution is now dominated by NaOH. Let's compare our pH values. Here we can see that we added 5 times 10 to the power of negative 5 moles of NaOH, and the pH only increased by 0.34 units due to the pyridinium ions maintaining the pH by using up the strong base to create more pyridine. However, when we added approximately the same amount of base as the initial HA amount, you can observe that the buffer effect was gone. As you can see, the pH increased by 3 whole units. Now let's add a strong acid to our initial solution. We will add 5 times 10 to the power of negative 6 moles of HCl to the weak base pyridine. We can predict that the pH will decrease as we add more acid, making the solution slightly more acidic. However, the buffer effect will prevent the pH from fluctuating too much. Adding strong acid to our initial solution will decrease the amount of pyridine by 5 times 10 to the power of negative 6 moles as the acid reacts with pyridine to form more pyridinium ions. This also means the pyridinium ions will increase by 5 times 10 to the power of negative 6 moles as more of it gets formed when the acid reacts with pyridine. With our new equilibrium concentrations, we may now use the HH formula to find the pH. The pKb remains constant, and we can sub in the A and HA values into the formula to get the pOH and then subtract it from 14 to get the final pH of 9.94. As you can see, the difference in pH was very little between the initial solution and the solution with strong acid added. This is due to most of the HCl being used up by pyridine to form pyridinium ions, allowing less of the acid to contribute to the overall pH. Now, let's add 10 times the concentration of HCl to the initial solution. The buffer effect will still be present, so we can predict that the pH will not decrease by a factor of 10 compared to the last solution we calculated. Logic remains the same as before. In our ice table, we decrease the amount of pyridine and increase the amount of pyridinium ions by the same amount, which is the amount of HCl added, which is 5 times 10 to the power of negative 5 moles. The pKb is constant, and we can sub in the A and HA equilibrium concentrations into the formula to get the pOH and then subtract it from 14 to get the final pH of 9.78. As you can see, the pH only decreased by 0.18 units from the initial pH despite adding 10 times the concentration of strong acid. Now, let's increase the concentration by a factor of 10 once again and see how much the pH is affected. We can predict that the buffer will still exist since we have not yet crossed the initial concentration of pyridine, which is 5 moles. The logic is still the same as the previous slides, with pyridine increasing and pyridinium ions decreasing in concentration by the same amount as HCl added, which is now 5 times 10 to the power of negative 4 moles. We can now use our values from the ice table and sub them into the HH formula. pKb value is still constant, and we sub in our A and HA equilibrium concentrations into the formula to get the pOH and then subtract it from 14 to get the final pH of 9.16. The buffer effect is still in play as the pH only decreased by 0.8 units despite adding a lot of acid. This is due to pyridine using up the acid to form pyridinium ions, allowing less acid to contribute to the final pH. We can compare pH values and notice how the buffer effect plays a significant role in maintaining a pH. We can notice that increasing the concentration by a factor of 100 only decreased the pH by 0.78 units rather than 2 units under normal circumstances. We can observe that the buffer effect gets weaker as more strong acid is added, since there would be less pyridine, allowing more of the acid to contribute to the overall pH. Now let's talk about pyridine spontaneity. In other words, whether or not the formation of products is spontaneous or not at room temperature, which is 298 Kelvin. So here we have our Gibbs free energy equation. Delta G is equal to negative R times T ln K. So what's given? Since R and T are always constant, the Kb value affects delta G. Since the Kb value is really small, this indicates that this reaction is non-spontaneous. When we put all our values into the equation, we get positive 50.03 kilojoules per mole as delta G at a temperature of 298 Kelvin. So, what does this number mean? The more negative the G value, the more spontaneous the reaction is, meaning that the formation of products is favored. Since pyridine has a positive G, it requires an input of energy in order for it to dissociate into conjugate acid and OH. This makes the dissociation of pyridine an endothermic reaction, as heat is required to push the reaction forward. Hence, the H value would also be positive. Therefore, the dissociation of pyridine is non-spontaneous and endothermic. The entropy of pyridine is 177 joules over K per mole. Entropy is a measure of the amount of molecular disorder. Heat creates entropy since it leads to more disorder in a system as molecules move further apart. So what does this number mean? This means that 177 joules of energy is required for every 1 Kelvin increase of temperature to disrupt pyridine structure. This means that the formation of pyridine created more disorder as the reaction moved from the reactants to products. Where is pyridine found? Pyridine is not abundant in nature except for the leaves and roots of belladonna and in marshmallow. Pyridine occurs in coal tar, which is its principal source before development of a synthesis based on acetaldehyde and ammonia. The pure substance is a colorless, flammable, water-soluble liquid with an unpleasant odor. Today, it is synthesized on the scale of about 20,000 tons per year worldwide. Pyridine is used as a solvent and to make many different products such as medicines, vitamins, food flavoring, pesticides, paints, dyes, rubber products, adhesives, and waterproofing for fabrics. Many of the foods that you eat have flavors that are the result of complex compounds that contain pyridine. Pyridine is used as a polar, basic, low-reactive solvent. It is especially suitable for dehalogenation, where it acts as the base of the elimination reaction and bonds the resulting hydrogen halide to form a pyridinium salt. Pyridine is also used as a base in condensation reactions. Pyridine is also mainly used to create herbicides, insecticides, and fungicides, as well as antiseptics in dental products. Paraquat is one example of a herbicide that contains pyridine. Pyridine moieties are often used in drugs because of their characteristics such as basicity, water solubility, stability, hydrogen bond forming ability, and their small molecular size. Because pyridine rings are able to act as the bioisosteres of amines, amides, heterocyclic rings containing nitrogen atoms, and benzene rings, their replacement by pyridine moieties is important in drug discovery. Pyridine is also a toxic molecule. Pyridine is harmful if inhaled, swallowed, or absorbed through the skin. Effects of acute pyridine intoxication include dizziness, headache, lack of coordination, nausea, salivation, and loss of appetite. They may progress into abdominal pain, pulmonary congestion, and unconsciousness. I was interested to learn more about pyridine because its structure is very similar to that of benzene, a molecule I've learned about in class. Pyridine and benzene are isoelectronic molecules, meaning that they have the same chemical structures and electron configurations. Despite all their similarities, pyridine has a completely different chemical property. Benzene is nonpolar and neutral, while pyridine is polar and basic, and also soluble in water. I was also interested to find out that pyridine is widely used for pesticides and antiseptics because it is a toxic chemical for humans, which I found concerning since the chemicals in pesticides find their way into the water system and they can potentially affect all animals, plants, and humans that consume that water. This brings us to the end of my presentation. I hope you enjoyed and have a great day.